This video is about Keto-Enol Tautomerization, which is kind of a strange little idea. It's basically an acid-base reaction mixed with resonance. Or more precisely, what you have to do is an acid-base reaction followed by some resonance thing happens, followed by an acid-base reaction. And so what it's kind of analogous to is resonance, really. But notice that what we're doing is we're moving a hydrogen, red here, to blue there. So it's not actually resonance, but instead we're plucking off that hydrogen, resonance happens, and we're sticking the hydrogen back on, or at least that's the idea. But this is actually a really useful topic to dwell on for a little bit because it basically forces you to get the acid-base chemistry right. This can happen under acidic conditions, this can happen under basic conditions, and the main reason why this will have a tendency to happen is if you have a double bond like that, carbon-carbon double bond, it's not as strong as a carbon-oxygen double bond, so you can transfer to here if you want. On the other hand, this kind of arrangement of electrons can perform chemistry that this can't. So this can access that if need be, and it can end up here. Bear in mind that the equilibrium will lie in the direction of the ketone. This is called an enol because you have an alkene, you have a double bond, and you have an alcohol bound to that double bond, so that combination is an enol. Bear in mind though, for nomenclature reasons, anywhere where you have a double bond is an alkene, and anything you have an alcohol is an ol, so enol just means double bond alcohol together. Although frequently when someone says enol, what they mean is oxygen directly bound to the double bond. So the OH is bound to the double bond. And that's specifically the usage I'm using here. If you have an oxygen bound to the double bond, then that is fundamentally the same as a ketone and can rearrange to achieve that. Or alternatively, an aldehyde if it was at this position instead of internal. But in any event, what happens to get from there to there is an acid-base reaction, some resonance, and another acid-base reaction. And that process is called tautomerization. So keto-enol tautomerization is the interconversion of an enol and a ketone via acid-base, resonance, base, and acid. Alright, down here what I have is the acidic setup. So let's pretend we're using sulfuric acid, and let's pretend we're using some water. And of course, if you have sulfuric acid, there's always going to be a little bit of water present in the bottle. So this is 98% sulfuric acid and 2% water in concentrated sulfuric acid. Obviously, if you're using less concentrated acid, then you can go ahead and do this with even more water. But the first thing that happens when you have a bottle of sulfuric acid, and it happens before you put your enol in, is you make H3O+. And so just bear in mind that if you have a bottle of acid of any variety, any kind of HCl, HBr, HI, nitric acid, anything else, you have some water present, and this reaction will take place before you even introduce your organic material. And so when you have sulfuric acid present, the thing that actually does the reaction with your stuff is almost certainly H3O+. And if you have HCl present, it's probably H3O+. You get the idea. H3O+ is the thing that's actually reacting because the strong acid and water will interact with each other first and make H3O+. So in any event, we have H3O+. The nearby double bond can come and abstract this hydrogen, and that will remake your water. However, this is far more likely to happen because the nearby oxygen has a pair of electrons that it can donate into this system. In other words, the reason why this double bond is quick to react is because you can take a pair of electrons from the oxygen and kind of force the double bond to react. So again, what's happening here is a sequence of 3 arrows. The oxygen is pushing down, which is causing this double bond, specifically this position of the double bond, to pull off that hydrogen. The OH bond is breaking and becoming an oxygen lone pair, and that leads to, at least in the immediate short term, a pair of resonance structures. So the pair of resonance structures that's formed is the obvious one that's caused by the oxygen kicking down as drawn, which leads to this material right here. However, if you had chosen only to use the double bond in the attack and you hadn't used this pair of electrons to kick down, then you might have arrived at this resonance structure first. It does not matter. Pushing this set of electrons between the carbon-oxygen double bond up to be a lone pair will reveal, of course, that you have this resonance structure right here, and taking that pair of electrons and kicking it down will reveal that you have this resonance structure as well. But the one that's useful for the purposes of the tautomerization is, of course, the resonance structure that looks more similar to your final product. So in other words, you probably want to use those electrons to cause this to happen in the first place, which then this will react to lead directly to your ketone, but it doesn't matter because you can achieve the outcome either way, depending on how you draw the arrows at this stage. Removing those resonance its arrows for the moment so as to clarify things a little bit. The water can come by and abstract this hydrogen, and when it does so, it will lead to the product as drawn right there. So that's obvious. If you simply pull off that proton, there you are, ketone, you are done. What's a little less obvious maybe is how the process works here, but if you were to come by and abstract this hydrogen, that can only happen if these electrons kick down right there. You cannot make the O-, you instead have to solve the problem immediately. I would prefer using this set of arrows right here because it's obvious that this hydrogen is ready to be abstracted. However, this set of arrows is equivalent and does lead to the ketone as drawn. And so under acidic conditions, you will note that at no point do I have an O- drawn anywhere. This happens first so as to lead to an oxygen that's plus, or alternatively a nearby carbon that's plus, no matter. Then you do the acid base. So first you do an acidic attack, and then you do a basic step. So under acidic conditions, first you protonate the molecule that's tautomerizing, then you consider the resonance possibilities here, if you didn't do so already in the first step, and then you do a basic attack to remove the extra hydrogen to lead to the new product. And again, the OH now is this pair of electrons right there. This double bond is now bounded to that hydrogen right there. And what you have essentially done is substitute the hydrogen from red to blue, but notice that the electrons didn't make the transfer. All you've done is take that hydrogen off, move the electrons, and stick it back on. In many ways, the acidic tautomerization is the harder one to see. The basic one is a little bit more straightforward to see. Under basic conditions, of course, you already have an O- around, so it is relatively straightforward to simply abstract the hydrogen that you see above. Mechanistically, what I would prefer to do is push those electrons onto the oxygen itself as a third lone pair. Therefore, the product that I'm going to draw in the immediate short term has 2 lone pairs on it initially, and now we have 3 lone pairs on it. So this material now exists in a resonance form that pushes electrons like so. And again, mechanistically, it's probably easiest to see what's happening if you start with the material that more closely resembles the product that you're headed toward. And so if you draw this resonance structure, you can recognize that this pair of electrons will simply abstract a hydrogen from the nearby water that you just generated, and that will lead on to the ketone, and there's your final product. Alternatively, of course, you can get there directly from this resonance structure if instead of drawing the resonance form, what you simply do is have the pair of electrons from the oxygen kick down and cause the double bond to go ahead and attack. And so this would then lead to the exact same outcome as long as this both set of arrows happens at the same time. Because again, what you need to do under basic conditions is have minus charges as opposed to neutral or plus charges. So your initial basic abstraction will remove that hydrogen to make an O-. You can either draw it this way or this way. You could draw 2 sets of arrows that lead to there. One of these 2 resonance forms will then interact with the water to pull off that hydrogen and to lead to the desired ketone. So what you're doing, of course, in the basic step is you're doing the base deprotonation first, contemplating the resonance, and then doing an acidic attack. So this serving as a base, acting on water as an acid to finish things off. And once again, you are removing this red hydrogen and you are plucking it on there, but the pair of electrons remains and the hydrogen simply moves from that position to that position. Now bear in mind, what I've illustrated for you in both cases is going from the enol to the ketone, but it's entirely possible that you could go from the ketone to the enol. And so my advice would be to practice both sets of mechanisms. Draw out going from the ketone to the enol under acidic conditions. Draw out going from the ketone to the enol under basic conditions. You're going to find that it's challenging to think about, but if you can get these 4 problems down, then what you have is a pretty good understanding of acid-base chemistry, and that's something that proves elusive for many students. So practice your keto-enol tautomerization, and a lot of mechanistic understanding will be unlocked for you.